Hexagonal recursive tessellation for irregular shape filling. Aaron Cattell, Department of Mathematics. Abstract. This paper presents a recursive hexagonal packing algorithm for approximating the area of irregular, simply connected regions in squared. The method employs a greedy strategy, placing the largest inscribable regular hexagon within the bounded region, then iteratively filling remaining space with progressively smaller hexagons following a geometric scaling sequence. We establish theoretical bounds on coverage efficiency, prove convergence properties, and analyze computational complexity. The algorithm achieves coverage ratios approaching unity as the minimum hexagon size tends to 0, with convergence rate dependent on the scaling factor. Applications include area estimation, adaptive mesh generation, and spatial discretisation for numerical methods. 1. Introduction. The problem of filling an arbitrary irregular shape with regular polygons has significant applications across computational geometry, computer graphics, finite element analysis, and approximation theory. Traditional tessellation approaches, while elegant for regular regions, encounter fundamental difficulties when confronted with irregular, non-convex boundaries. We propose a greedy recursive approach that exploits the remarkable packing properties of regular hexagons. The algorithm proceeds by placing the largest possible hexagon within the target shape, then iteratively filling the remaining space with smaller hexagons until a specified minimum size threshold is reached. This method combines theoretical tractability with practical efficiency. 1.1 Why hexagons? Regular hexagons possess several properties that make them uniquely suited for this application. Optimal packing efficiency. The honeycomb conjecture, proved by Hales, 2001, establishes that regular hexagons provide the least perimeter way to partition the plane into equal areas. For our purposes, hexagonal packing achieves approximately 90.69% coverage when inscribing circles, and 100% for pure hexagonal tessellation. Isoperimetric optimality. Among all regular polygons that tessellate the plane, hexagons have the smallest perimeter-to-area ratio, minimizing boundary effects in our approximation. Rotational flexibility. The six-fold symmetry of hexagons provides multiple orientation options when fitting into irregular spaces, though our algorithm employs a fixed orientation for simplicity. 2. Formal definition. 2.1 Problem statement. Let omega proper subset symbol squared be a bounded, simply connected region with piecewise smooth boundary del. We seek a finite collection of regular hexagons H equals the H is such that the coverage ratio is defined as. Our objective is to maximize rows subject to a minimum hexagon size constraint. 2.2 Hexagon geometry. A regular hexagon with circumradius r, distance from center to vertex, has the following properties. Area A equals 3 square root 3 2 r squared almost equal to 2.598 r squared in radius apothema equals square root 3 2 r almost equal to 0.866 r side length as equals r perimeter tongue poking smiley equals 6r. 2.3 The recursive algorithm. We present the core algorithm in pseudocode. Algorithm 1. Greedy recursive hexagonal filling. Algorithm 1. Greedy recursive hexagonal filling. Input. Irregular region omega, minimum hexagon radius r_minute. Scaling factor alpha. Input. Irregular region omega, minimum hexagon radius r_minute. Scaling factor alpha. Output. Set of non-overlapping hexagons H proper subset symbol omega. Output. set of non-overlapping hexagons H proper subset symbol omega. 1, H1, H. 2, our initial radius, omega, largest inscribable hexagon 2, R. 3, while r greater than or equal to r underscore minute do 3, while r greater than or equal to r underscore minute do. 4, repeat 4, repeat. 5, p find valid placement, omega, h, r 5, p find valid placement, omega, h, r. 6, if p not equal to null then 6, if p not equal to null then. 7, h underscore new hexagon, center equals p, radius equals r, 7, h underscore new hexagon, center equals p, radius equals r. 8, h union set symbol, h underscore new 8, h union set symbol, h underscore new 9, end if 9, end if. 10, until p equals null 10, until p equals null. 11, our alpha times our reduce hexagon size 11, our alpha times our reduce hexagon size. 12, end while 12, end while. 13, return h 13, return h. The subroutine find valid placement searches for a position where a hexagon of radius r can be placed entirely within omega without overlapping any existing hexagon in H. 3. Theoretical analysis. 3.1 Scaling relationship. Let R denote the radius of the largest hexagon placed. Subsequent hexagon sizes follow a geometric sequence determined by the scaling factor alpha set membership symbol 0, 1. Where K indexes the size class, not individual hexagons. The area of hexagons in size class K is. 3.2 Convergence analysis. Theorem 1. Convergence. For any bounded region omega with area, omega, 0 and any epsilon, 0, there exists r underscore minute, 0 such that the algorithm achieves coverage rho, 1 epsilon. Proof. The uncovered area, after the algorithm terminates, consists of regions where no hexagon of radius greater than or equal to r underscore minute can be inscribed. Each such region has diameter at most 2 r underscore minute. The number of such regions is bounded by area, omega, / r squared underscore minute. Thus the total uncovered area is O, r squared underscore minute times r squared underscore minute, equals O, 1, as r underscore minute 0, but more careful analysis using the boundary length shows it is O, r underscore minute. 3.3 Number of hexagons. Theorem 2.4 Scaling factor alpha and minimum radius r underscore minute, the number of size classes is. The total number of hexagons depends on the geometry of omega, but is bounded by. 3.4 Optimal scaling factor. The choice of alpha involves a fundamental trade-off. Scaling factor advantages disadvantages large, e.g., 0.9, finer gradation, better gap filling more iterations, slower convergence small, e.g., 0.5, faster size reduction, fewer iterations may leave larger gaps. Proposition 1.4 Regions with smooth boundaries. The empirically optimal scaling factor is alpha asterisk, almost equal to 0.7, balancing coverage quality against computational cost. 4. Coverage bounds. 4.1 Interior coverage. In the interior of omega, away from boundaries, hexagonal packing approaches optimal efficiency. Theorem 3.4 Any convex region omega within radius r, the algorithm with r underscore minute 0 achieves asymptotic coverage. 4.2 Boundary effects. The primary source of uncovered area is the boundary region. For a region with perimeter L and minimum hexagon radius r_min, where C is a constant depending on boundary curvature, approximately C almost equal to 1 for smooth boundaries. 5. Computational complexity. 5.1 Containment testing. For a polygonal approximation of del with V vertices, testing whether a hexagon lies entirely within omega requires OV, point-in-polygon tests, 1 per hexagon vertex. 5.2 Overlap detection. Testing overlap between a candidate hexagon and M existing hexagons can be performed in O(m) time using center distance checks, or O log m, with spatial indexing structures. Theorem 4. The algorithm terminates in O(n squared times V, time without spatial indexing, or O(n log n times V, with a quad tree, or R-tree structure, where n is the final number of hexagons. 6. Application, area approximation. The hexagonal filling provides a natural area approximation, where _expected can be calibrated using regions of known area. 6.1 Error analysis. The approximation error satisfies. This provides first-order convergence in r_min, comparable to Riemann sum approximations with step size r_min. 7. Extensions. 7.1 Adaptive scaling. Rather than fixed geometric scaling, one may adapt alpha based on local geometry, using smaller reductions near complex boundary features, and larger reductions in open interior regions. 7.2 Mixed polygon filling. Combining hexagons with triangles at boundaries can achieve 100% interior coverage while better approximating curved boundaries. 7.3 Three-dimensional extension. The natural 3D analog uses truncated octahedra, which tessellate cubed and possess analogous optimality properties, Kelvin's conjecture, though superseded by the Ware-Phelan structure for foam-like partitions. 8. Conclusion. We have presented a recursive hexagonal filling algorithm with proven convergence properties and analyzed complexity bounds. The method provides an intuitive geometric approach to irregular region coverage, with the coverage ratio approaching unity as the minimum hexagon size decreases. The algorithm's simplicity, combined with hexagon's optimal packing properties, makes it suitable for applications in area estimation, mesh generation, and spatial discretization. Future work should address adaptive scaling strategies, rigorous analysis for non-convex regions, and parallel implementation for large-scale applications. References: 1. Hales, T. C. 2001. The Honeycomb Conjecture, Discrete and Computational Geometry, 25, 1-22. 2. Toth, L. F. 1964, Regular Figures. Pergamon Press, Oxford. 3. Conway, J. H. and Sloan, N. J. A. 1999, Sphere Packings, Lattices and Groups, 3rd ed. Springer Verlag, New York. 4. Ware, D. and Phelan, R. 1994. A counterexample to Kelvin's conjecture on minimal surfaces, Philosophical Magazine Letters, 69, 107-110. 5. Umount, D. M. and Arya, S. 2010. Computational Geometry, Proximity and Location. In Handbook of Discrete and Computational Geometry, pp. 767 to 791. CRC Press.